Welcome, everyone, to the AI Reading Group from Women in AI and Robotics. My name is Cleo Norris, and I created and I host this group. We're really excited to create a space for direct dialogue between researchers and the community to allow for deeper engagement with emerging research. So with that, I'm excited to introduce our speaker. Bingbin Liu is a research fellow at the Kempner Institute at Harvard University. Her research interests focus on the theoretical and scientific foundations of machine learning, particularly in questions related to language models and self-supervised learning. Before joining Kempner, Bingbin was a postdoc research fellow at the Simons Institute. She received her PhD in machine learning from Carnegie Mellon University. Today, she'll be presenting the paper Exposing Attention Glitches with Flip-Flop Language Modeling. So with that, I will pin you, Bingbin, and you can feel free to share your screen. Okay, there we go.
Are people seeing my slides fine? I'm gonna
Yes, we can. Yeah, we can. It's in presentation mode now.
Awesome. Thank you very much. Well, thank you very much, Cleo, for the introduction, and thank you so much for having me here. I'm really excited about this initiative where we're trying to bring more diversity in the community, especially in a very turbulent time. So today I'm going to talk about our work exposing attention glitches with flip-flop language modeling. Oh, sorry. And before I start, I want to say that I welcome question anytime in the talk. I may not be able to see the chat very like in time. So if you have questions, please feel free to just shout out your question. All right, so back to our work. This is work done with my amazing mentors, Jordan, Servi, Akshay, and Cyril. One motivation we kind of have for this work is that we're curious about why there are occasional errors in the language models, even though the language models are quite capable themselves. So for instance, here is one output that GPT-4o gave me last week. It's clearly making some simple mistake, even though 4o is quite useful already. Then in today, we'll talk about one explanation for this kind of occasional errors, which we'll call attention glitches. We will expose attention glitches by stress testing using a very simple task called flip-flop. We'll see that this kind of inherent glitches are related to inherent limitations of attention. And also we'll discuss some mitigations and also next steps. To provide more context, this work is part of the project that we did on trying to understand how transformer can perform sequential reasoning. We have two types of results. The first one is capability, and the other is limitation. For capability, we show that transformer is capable, in theory, to solve a broad class of reasoning tasks. But in practice, we also find that if we are training the model from scratch on some limited data, then these transformers often struggle to find a solution, even when the task is very simple. For today, our focus will be on the limitation, but we'll also talk about the capability part briefly as a background. We'll start with defining what is reasoning problem. Our focus will be sequential reasoning, and this could take various forms. For example, this could be to perform arithmetics where we're trying to multiply several numbers one by one. It could be logical deduction. It could also be, say, we're trying to trace the value of a variable in a program. And despite all the various forms of sequential reasoning, we can abstract them into modeling sequential state transitions. To show you what I mean, let's say we're dealing with the arithmetic task. Here we can map the number 1 and -1 into -1 to the power of 0 or 1. And then to compute the product, it's equivalent for us to track how the exponents of these numbers change. And we can do so using a two-state machine where the two states are even and odd, and the input could be 1 or 0. We will toggle the state when we see 1, and we don't change the state when we see 0. We call this two-state machine a parity counter. And this parity counter is a special case of a general finite state automata. For the general case, we define a finite state automata A using 3 components. The state space Q, the input alphabet sigma, and also the transition function delta. For the parity counter we saw, the two states, both the state space and the alphabet are gonna be binary. Oh, I see some chats and I just wanna make sure. Okay, thanks, yeah. Oh, yeah, so the state and the alphabet are both binary. And then in automata, we will model the dynamics by following the transition function delta. In particular, at each time t, the transition function delta will take in the previous state qt minus 1 and the current input sigma t and transition to a new state qt. So in this view, we are modeling one state transition as one reasoning step. And we can think of sequential reasoning as corresponding to simulating the automata. In our prior work, we showed that transformers are capable of simulating automata. And the main idea is that we're using some results by Kern and Rhodes, which says that an automata A can be decomposed into two base vectors. And the connection between this two transformer is that each of these base vectors can be represented by one transformer layer. The first type of base vector is a mod counter, and this is a generalization of the parity counter we saw earlier. For parity counter, we're taking the mod of 2, but for mod counter, it could be the mod of some general prime P. This mod counter can be represented by one layer of uniform attention, and the idea is that the attention will sum up all the inputs, and then the MLP will perform the mod function. And the second type of base vector is a memory unit. So in the example we are showing here, we still have 2 states, but now we have 3 inputs. If the input is club or diamond, then we'll set the state to be club or diamond. Or if the input is no op, then we state where we are. And the reason that we're calling this a memory unit is that we can think of the club or diamond as writing 1 bit of information to a 1-bit memory. And then the no op corresponds to reading from the memory. For this memory unit, we can represent it using one layer of sparse attention, where the attention will sparsely put on the most recent write operator. For today, we'll be focusing on the second case, and that is the memory unit. So just to checkpoint where we are, we talk about using automata to model reasoning. We saw that transformer can efficiently simulate each of these 2 base units. And in particular, the second type of base unit of the memory unit, and that's the thing of our interest. In the second part, we'll see that despite the theoretical possibility of modeling such automata, in practice, transformers often fail to find an optimal solution. I'm again seeing a chat. Okay, so the question in the chat is that, can MLP do mod operation? And the answer is yes. So exactly in the first part, when we're trying to model the mod counter, then the mod operation is done by the MLP. Okay. Oh, and then for future, if you have questions, feel free to just shout out and then we can pause. All right. Okay, so for the second part, we're talking about this limitation. And the main idea is that we're gonna construct a simple language based on the memory unit. Our focus will be the 1-bit version of the memory unit, which is also known as flip-flop. We can think of this to be toggling between 2 states. Then given this, our language, the flip-flop language, is going to consist of sequences of instruction value pairs. There will be 3 instructions: write, ignore, or read. Each instruction will be followed by a binary value 0 or 1. The value could be anything except that the value following the read must be the same as the value following the most recent write. And the idea here is that if we're trying to read from the memory, then the value we read should be the same as the one that we wrote into the memory. To give an example, say in this case, the first read is getting the correct value, whereas the second read is wrong. So in the experiment, the model will be trained to predict the value following the read. And before we go to the experiments, I want to motivate why why we care about flip-flop. We already saw this one case from the automata setting, and I also want to say that this flip-flop is actually an atomic unit, not just for automata, but for a lot of reasoning tasks in practice. So to give some examples of real-world settings, say for the ignore operation could show up as irrelevant context or distractors in the language. For instance, in this case, when we're trying to determine the state of the keys, then the other tags are going to be irrelevant and should be ignored. And similarly, the write operation could be considered as updating the semantics, say in code. In this snippet I'm showing here, if we change the semantics of the built-in operator in Python, then this change will be reflected later when we're using this built-in function. And in addition to the kind of very a very direct translation of flip-flop to real world, we can also connect flip-flop broadly to other abilities that we care about. One example is induction head. So flip-flop is actually a very simple case of induction head. And the reason is that when we're trying to solve the value following the read, we're effectively asking the model to find the most recent occurrence of write. And this is a fixed pattern we're going to check. Flip-flop could also be used to model long-range dependency, because in this modeling task, the hardest case would be when the read and the write are very far from each other. Another example that people may care about is closed domain hallucination. So here, closed domain means that the generation of the model is contradicting directly to something in the inputs. And we can see that in this case, the value following read is contradicting the value following write. So this is one example of closed domain hallucination. In addition to being an atomic unit that's very universal in practice, another reason that we may care about flip-flop is that it's the cleanest setting that's still interesting to study failure modes. So if we compare to prior work, then there are two main types of tasks studied in prior work. The first type of tasks, I consider them as very simple, but it could be less interesting because they can be solved by a fixed attention pattern. So examples include the parity task, where we can use a uniform attention, or there's something called first, where the label of the sequence is given by the first element in the sequence. The second type of the prior work tasks would be more complicated tasks. So people have studied this for formal languages, algorithmic reasoning, code and math, and some things in natural languages. As we argued earlier, flip-flop will be a subtask that's very likely embedded in these more complicated tasks. And the simplicity of flip-flop would make the failure mode of flip-flop more jarring in practice. Okay, so now I'm gonna formally define what we are doing for flip-flop, and then we'll see the experiments. I want to pause briefly to see if there's a question. All right. Yeah, so the task we're going to use for flip-flop is called flip-flop lineage modeling. The task is that we're training the model to predict the value following the read, and we'll also evaluate the model only on the value following the read. This is a task that's fully determined by the context, and also the training signal is very clean. So it should be a very simple task, since the model is trained only to produce the value that has unique values, rather than, say, for the ignore, where where there could be a probability. The data distribution we'll use will be parameterized by the probability of seeing an ignore, and that is P of I. In the following, we will vary this P of I during train and test. So we'll be checking the OOD performance of the model. The probability of seeing a write and a read will be equal, and they're dividing the remaining probability mass. And then the two binary values that can follow each instruction would also be split half-half. In all the experiments, we're fixing the sequence length to be 512. So this is just a same length generalization task. There's no length generalization. Specifically in the experiments, we're using P of I to be 0.8 during training and using P of I to be 0.98 during testing. And this 0.98 means that the testing sequences are going to be sparser in the number of writes. And to convince you that this is indeed a very simple task, let's first see how RNN will perform. So this is the results from a one-layer LSTM. We can see that within 200 training iterations, the model can reduce the error to 0 very quickly. And this is the error for both in distribution and OOD. In contrast, for transformer, it needs much more resources to learn. Here, each panel corresponds to one configuration of the transformer. By default, we'll be using this transformer here with 6-layer 512 dimension and also 8 heads. But in the experiments, we're varying the model size from 2 to 8 layers and also varying the dimension from 128 to 1000. We can see that almost all the transformers can reduce the in-distribution error to be very, very low. So it's training properly. However, the model will struggle to do well in OOD. the OD lines are these red lines, and we can see that they are far from perfect. I do want to mention that the y-axis is actually quite is on the log scale, so the model is still performing reasonably well. So most of them have more than 99% accuracy, but it's still far from perfect. And this is especially in contrast to LSTM, which can reach zero error very frequently, very fast. And this phenomenon that the transformer is suffering from occasional errors on this hard retrieval, we call this to be attention glitches. The results we just saw are for LSTM and for transformer. For those of you who are curious about other models like the state space models, we didn't do this ourselves, but there's a later paper that tried the flip-flop experiments on Mamba. And they found that Mamba is closer to LSTM than to transformer, and Mamba can also learn this perfectly within very few iterations. Okay, so what we just saw is that attention glitches happen in transformers, and they have this very long tail of errors. I want to mention that these kind of long tail errors still exist even if we go to the state-of-art models. For instance, we can explain what the game is to ChatGPT, and then we can ask ChatGPT to answer for a length 512 sequence. So the GPT-4o performance, and this is something I tried in September. For that case, I think GPT-4o is giving chance level performance. I also played with O1 yesterday, and we saw that O1 get about 90% accuracy. And this 90% is based on 10 trials. It failed on the first one. So if we keep running, it might not be 90%, but it's like, so based on the limited try, we see that it's not perfect. Okay, so now we know that attention glitches happen. Can we understand why it happens? First, I want to clarify that it happens not because of limited representational power. In fact, we can show that this very simple flip-flop task can be solved by a two-layer one-hat transformer. The main idea is that the first layer will attend all the writes and also find the value following these writes. Then the second layer will tie break between different writes by using the positional information. And this is also a similar idea that people use to construct a solution for induction head. Okay, so now that we know it's not due to representational power, what is it? In the following, we'll see two potential causes, each correspond to one type of OOD failure. The first type of OOD failure would be the case where we go to denser sequences, and these are sequences with more writes. We call this diluted stop attention, in the sense that the way we are trying to solve the flip-flop is by asking softmax to approximate a hardmax. And this hardmax is now given by the output of this softmax, where the denominator will include a bunch of writes that the model needs to find first. And so when we move to denser sequences, there will be more and more items accumulating in the denominator so that the hardmax approximation will be pushed away from 1. And this kind of problem has also been identified in prior work. And one way for us to fix it is to instead use a hard attention. But even if we use hard attention, it could solve this case. It still cannot solve a second failure case. That is when the positional information will dominate the content. In this case, we move to sparser sequences where there are fewer writes. The main idea here is that even though the length of a sequence is fixed across train and test time, there is still some implicit length generalization happening in the sense that the distance between the read and the most recent write could be increasing from train to test time. What this causes is that the model can wrongly attend to a position that it shouldn't be attending to. One example is this. So here we're showing the attention map of a transformer. And here the x-axis, or like the columns, correspond to different previous positions. And each row will correspond to the attention map for one of the current position. For this example, we have a write at the very beginning of the sequence. And we can see that for a lot of the positions, they are correctly attending to the initial position. However, as the model goes to later positions, it starts to drift the attention. Now the attention is still very sharp, but it's sharp on the wrong position. So now we have this two mechanisms through which attention glitches could happen. One is the diluted self-attention, and the other is the wrong position over the content. Then the question is, can we mitigate this? For the mitigation part, we'll look at two main types of mitigation. The first one will be the more direct control over the data or scaling resources. And the second one will be some somewhat indirect control in the algorithm that we're using. For the direct control part, we can either incorporate OOD data directly or to scale up the resource. And I'll focus on the OOD data directly part. So this part is kind of a cheating solution, but this does provide us a performance ceiling. And also in practice, it has been found that we don't need a lot of OOD data in order to improve the OOD performance. For example, prior work by Gelasi et al., they found that even introducing a few samples from OOD can drastically improve the performance, and they call this to be priming. For scaling part, we try scaling different resources in terms of the model size, the number of data we see, or the number of iterations we use. The idea is that if we're using more and more fresh samples, then hopefully we're also covering a wider range of the problem space. So hopefully it could also introduce some OOD data as we sample from the same distribution. For the algorithmic control part, we tried two main strategies. The first one is regularization. So this includes both the normal one that includes weight decay or dropout, and we also introduce some task-specific attention sparsification regularization. We also play with different architecture choices, including various positional encoding and also activation function. The results are summarized in this plot over here. So here, the two axes correspond to two types of OOD errors. The x-axis correspond to errors on denser sequences, and y-axis correspond to errors on sparser sequences. The error is lower if we go down or go left. And here, each dot corresponds to one train transformer. The coordinates is given by the two errors of a transformer. We can see that all of transformer, they are doing reasonably well. They're getting more than 90% or even 99% accuracy. However, all of them are far from the origin, which corresponds to zero error. I also want to point out that the zero error corner is not unattainable. For example, we can easily achieve zero error using a one-layer LSTM. And next, we're going to dive into the details for the mitigations. The punchline is that these kind of mitigations are not very effective. They can help with either type of the two errors, but not both. We will show the errors in the two panels. The top panel corresponds to error on sparser sequences, and the bottom panel corresponds to errors on denser sequences. To start with, we have the baseline performance from the 6-layer transformer, and also the performance ceiling. The ceiling is given by either LSTM or training directly on OOD data. Then for the direct control of scaling, we can see that scaling is helping to reduce the error on the sparser sequences by a little bit, but at the same time hurting the performance on denser sequences. And similarly for the regularization, we try. So here we're showing regularization using weight decay or some dropout. One interesting thing we found is that using a large dropout on the embedding seems to be very effective. We don't know exactly why, but our hypothesis is that it's probably because when we're dropping out on the embedding, then we're decorrelating the content and the position, and this could help with generalization, especially on the sparser end. And here we're showing different mitigations by changing either the positional encoding or the activation function. We found that using relative positional encoding seems to be helping with the denser sequences a lot, which kind of makes sense because when for denser sequences, you only care about the one that's closest to the current position, and this might be easier to capture when we're using relative positional encoding. We also mentioned that in addition to the regular regularization, we also try something that's specific to the task. That is, we're encouraging the model to learn sparse attentions. I want to say a few words about this. Here we're using different type of regularizer that could be either the entropy or the LP norm of the attention pattern. We can try to see how this affects the trained model. So here we have the attention pattern on one layer, one head models. We can see that when it's trained without the regularization, the model is correctly picking up the right positions, but it's not tie-breaking between the rights in the sense that it's not telling apart which one is the most recent. If we impose the regularization, then we can see that now the attention pattern becomes very sharp and very clean. However, I want to mention that having a sharp attention does not mean that the model is always correct. For instance, here we have one example where the attention is one hot, but it's still wrong. And this kind of echoes our earlier point that hard attention can improve in some cases, but it doesn't fix everything. Now, going back to the mitigations, we already saw some examples where the mitigation can help on the denser sequences and some can help with the sparser sequences. What happens if we combine both? It seems that when we combine both, so in this case, we're combining different change of the activation or position encoding, as well as the regularization such as dropout or sharp attention. In this case, it seems that the combination is still only helping one of the two types of errors, but not both. In particular, for some reason, it's helping with the denser sequences a lot. So the main point that we're getting from all the mitigations is that there's a trade-off between the two types of errors. And by a lot of standard tricks that people have tried, we are not finding one mitigation that can effectively improve both types of errors. So to summarize, in this work, we look at one explanation of the occasional errors that could happen in Transformer. The mechanism we identify is attention glitches, which show that Transformer will struggle to do perfectly on hard retrieval tasks, even though the retrieval task could be very simple. For instance, on this flip-flop language, we saw that Transformer exhibit a long tail of errors. In contrast, LSTM can solve the task very easily. So one immediate goal for us in the future could be to see how can we change the training procedure or the architecture so that we can make the model learn as well as RNNs. We also looked at why attention glitches could happen, and we found that this could be tied to some inherent limitations of the attention. One implication of this is that these errors are very hard to mitigate. Nevertheless, we found that it's quite effective if we improve the data that we use in training. And this improving the data idea has also been a recurring theme in the field recently. Okay, so that will be the end part of the talk. We saw briefly how to study the capability of the model in reasoning tasks, and the way to do that is by formalizing reading tasks using automata. Then for the limitation part, we saw attention glitches happen, which reveals inherent limitations of the attention. I'm about time for the talk part, so I will stop here, but I want to briefly mention some of the discussion point that we could be talking about. So I guess one point is about toward glitch-free models. We'll look at some examples that we can improve data or the architecture. And I guess one other thing I want to note is that in this talk, we are focusing on a notion that is not very common in most of the work. So in most work, we care about average error in the sense that if we're getting, say, like 99%, then we're happy with it. But in our work, we are focusing on the worst case error in the sense that we consider the model if a model is not achieving 100% accuracy, then we consider it to be glitching. Then one question we could talk about would be, do we really need to be this stringent? For example, one could quote Turing by saying that if we require the model to be infallible, then this model can't be intelligent. And we can argue that being intelligent would be the ultimate goal of our field. But also, I still want to slightly push back to this by saying that we still want to be aware of this kind of mechanistic errors that could happen, because there are cases where being intelligent is not our only goal. We still care about safety and robustness, and we need to be aware of such errors when we use the current models in some high-stakes scenarios. A second point I want to mention is that we could probably use more of this small-scale settings when we study machine learning. So here I'm calling the sandboxes, which are minimum representative abstractions of complex systems. So the reason we care about this is that by being very simple and small, these sandboxes make it easy for us to analyze them theoretically or do rapid iterations empirically. In today's talk, we look at this automata as one sandbox, and we can see that we can run over 10,000 transformer on them, which is not possible if we're doing large-scale models. So more broadly, I think this could be used in various scenarios, including scientific understanding, evaluation, and also using finding efficient solutions to the current problems. But we do also need to be aware of scale. Before scale, I want to plug in one small ad. So if you're interested in this idea of using sandbox to study the current method, then we have a NeurIPS tutorial on the same topic. So for those of you who are interested, we have a page collecting the resources. So despite the benefit of using small scale, we do also want to be aware that scaling is something that's very real and very beneficial. We already looked at scaling is not scaling is not going to solve everything, but it does help in a lot of cases. So I think it's going to be good for us to be mindful when we make design choices so that the method we develop in the small scale can also scale up properly. Okay, I'm exactly at time. I will stop here. Thank you.
Thank you so much, Bingbin. I'll unpin you. I think those talking points are really interesting too, especially kind of bringing in something similar to the Turing test in terms of how do we actually tell when something's intelligent, and is that the most important thing in development, which often it's not. But yeah, so this will start the Q&A portion of everything. If you don't feel comfortable unmuting and asking your question, feel free to pop it in the Q&A section. But if you do, please raise your hand and we can call on you. I think there was already one hand raised, so go ahead.
Oh, sorry, I accidentally lowered my hand, but thanks for the presentation. Kind of like one thing that I thought was very cool was that you showed that, like, why do you think like LSTMs perform like way better than transformers? Kind of like from what you said in the presentation, the two things I gathered was that kind of LSTM and I guess also Mamba deals a bit with like compressing the state a bit.
Yes.
So like that kind of like removes all the irrelevant information. But also like I guess there's a deeper discussion on like the probabilistic nature of transformer. Like basically it's designed so that the next token is like a probability thing. But yeah, what's your opinion there?
Oh yeah, great question. That's something we were also thinking about like when doing this project. I guess the short answer is that LCM or this recurrent models will be very suitable for the particular task that we care about here. So we can see that we are trying to model things by automata, and the definition of the transition function in automata fits almost perfectly to this recurrent structure. So that's probably the source of why like both LSTM and Mamba, why they are so effective for this particular task. And so one point you mentioned that's very interesting is the compression of states. So there has been work saying that for recurrent models, because they're bounded by the state size, so in practice so they might fail on some extremal retrieval task, like needle in a haystack. But that is not the difficulty of the task that we are handling here. For example, for flip-flop, we have this 1-bit information. So it's very light information for the model to memorize. And in that case, the typical criticism for these kind of recurrent models would not apply. So they perform very well. And then to the second point about transformer being probabilistic, that is a great point. That is not how we're training our model. So in the talk today, we talk about one type of training where we supervise the model only on the read values. And these read values are fully deterministic. So we're making it easier for the model to learn. In the paper, we also try a different setting where we use a typical we use a typical generative setting. In that setting, we will train the model to do next word prediction. And in that case, we can see that there will be some training signal that's more probabilistic in the sense that if we're at some position, then it's unclear what the next instruction would be or what the value would be. So there's some probability there. But for the experiments that we're showing up, that we're seeing in today's talk, everything is fully deterministic. So the model should not make mistakes, or like the mistake shouldn't come from the training signal being confusing.
I see. Thank you. Makes sense. Then in that case, would you argue that kind of like some I don't know, I'm kind of thinking whether there's like a simple modification to this problem which will make attention transformers perform better than LSTMs. Like, do you think there's something like that? Yeah.
Interesting. So I guess better, how do we measure better? Better, two things. One is the performance, and the other is efficiency, I guess. So currently, I think performance LSTM is at 100, so it's like we can reach it, but it's gonna be hard to surpass 100%. In terms of like training efficiency, because of how simple the task is, LSTM can train this in less than 200 steps. So we don't expect things to be faster than that. So I think like in that sense, we're not gonna beat LSTM on this particular simple task. But what we could hope for is to approach that. So one thing that's very like a very intuitive and reasonable change to transformer is to use chain of thought or scratchpad, so that we're now turning transformer also into a recurrent mode. We didn't do this in this paper, but we did this in the previous paper, which is quite related, and we believe that that would help. So in the previous paper, we tried more complex tasks, and then changing the transformer into a recurrent mode solve the task perfectly. It can reach the accuracy perfectly, but it still cannot train as fast.
Thank you. Yeah, that makes sense. Like, I think that also explains why O1 performs better. Yeah.
Oh, that's a very complex question. What O1 does? Okay. Okay, I think oh, sorry, could you elaborate on why you think this is related to how O1 is performing so well?
Oh, yes. So my understanding of how O1 works is that OpenAI made a reinforcement learning thing to generate chain of thought tokens in
Yeah.
order to solve the task, which is pretty much, I thought, what you said, like it basically putting the problem into chain of thought and like solving one step at a time. So yeah.
Ah, okay, I see. Okay, that's a very interesting point. So I guess like one thing I want to mention is that when we say that we use chain of thought, there are typically two arguments about why chain of thought could be helpful. One argument is that chain of thought will increase the representability of the model, and that's likely what's not what's happening here or in O1. And the other thing would be chain of thought could help with training stability, so it will help improve training, and that will be what happened in our experiments. And for O1, so if you're a training model by SFT, then it's probably likely why chain of thought is happening. For RL, I think chain of thought would probably also help with stabilizing training, but I know very little about RL training to make intelligent comment on that. But I think it's a very interesting future direction, or like a very interesting research question to think about.
Got it. Thanks for all the answers.
Thanks, cute cat.
Yeah, those were great questions. I think we have another question rolling in. So could you please touch more on the flip-flop modeling of the real-world tasks? You've mentioned it in the talk, but it would be great if you could talk more on it with some examples.
Oh, great. Yeah. I wonder if it's okay for me to bring back the slides so we can look at it.
Totally. Yeah, whatever we need to share.
Okay, thanks. So this will be, I'm just gonna go back to this, right? So I guess here we, okay. Okay, here are two examples of flip-flop. So I guess we can think of flip-flop as a memory task or a retrieval task. And it's a retrieval task that is context dependent. In our setting, we are deliberately making the task very, very simple so that we know exactly which is the thing that's to be retrieved. Then for more real-world applications, so here we have two examples. One is reflecting the ignore part, and one is reflecting the write part. For the ignore part here, so this is kind of task where the model is supposed to ignore all the distractors or like all the irrelevant context in the input, and then identify, in this case, the state of the key. For the write part, the thing that the model needs to do is realize that the semantics of something that is very likely have seen during training is now changed in the input. So the output of the code, in this case, the value of the sum of x, should reflect this change in the semantics. And I would also want to mention that for both examples here, there hasn't been a paper studying inverse scaling challenge. Sorry, there are several papers studying inverse scaling. And then, so these are two type of failure modes that people found that if you increase the scale of the model may perform worse on this. In the sense that like if you okay, so they're performing worse, but then there's also a paper saying that there might be a U shape in the sense that if you go to small model to medium-sized model, then you see a performance drop. But if you keep increasing the model size, then the performance can pick up again for some tasks. So I think that's one interesting case in practice. More broadly, I think connection to some other tasks, induction head is one case where we see very related, because now for induction head, what it does is that each time you see some token, you want to look back the previous occurrence of that token and then get the value right next to it. In our case, we're not doing exactly the same token, but we always have the same pattern that when we see read, we want to find the right. So in that sense, it's very similar to induction. And we can also see that the construction of the transformer that solved this task is also similar. Long-range dependency, for long-range arena, for example, they have a bunch of tasks, and then some other things I think is quite related is kind of needle in a haystack, or this kind of like retrieval task. In this case, we can think of it also as a retrieval task, because now the model needs to ignore everything in between and retrieve the task that is and retrieve the value that is written to the memory at the very beginning. And closed domain hallucination, I still don't have a good definition of hallucination, but in this very narrow context, we're saying that we kind of think of something to be hallucinating if the model is predicting some output that should be easily correctable from the input itself. So in this case, we're saying if the read value is contradicting the write value, then it's a direct violation of the context rather than some prior knowledge that the model might have. I'm not sure if I answered the question, so please feel free to speak up or ask follow-ups.
Yeah, put any follow-ups in the chat or unmute. Thank you, Bingbin. Okay, I think perfect. Yeah, keep your questions rolling in. In the meantime, I can ask a quick question. So basically, the paper proposes using FFLM as a stress test for sequence modeling architectures. So what advantages do synthetic benchmarks like FFLM offer over natural benchmarks, like the ones that use real world data? And what are their limitations?
Oh, yes, I love this question. Thank you. Because I think about this kind of small scale thing a lot. I want to bring up this slide to just show what are some of the plus over standard benchmarks. I don't show everything fully here, but I'll say like one thing is that now we have infinite supply of data. So we can generate data on the fly, and then that's very, very cheap. So we don't have to collect. And these are very, very small scale things, so that even people without a huge compute resource can still do these kind of tests. And also these tests are very controllable in the sense that we can precisely control the parameters that define a task. In our case, we saw that flip-flop have 3 instructions, 2 values, and some probabilities. We can each thing can be changed here, and we can also change the task to be more complicated by, for example, making the condition for retrieval of the value to be more complex. So it's very controllable, and we can steer it to different places to stress test the probability that we care about. I think that's one thing that we don't have if we are using standard benchmark collected from real data. The bottleneck, though, is that I think it's still a very synthetic case, so it might fail to cover something that's in practice. For example, if you do like for the synthetic setting we have, it's a very clean and simple setting, so it might miss some nuance in real world language. For example, if you're trying to see things like some ambiguity in the natural language, then that's something that's not present in the current benchmark, like we have from purely synthetic side.
Absolutely. Like the researchers basically have to come up with any kind of case that happens, and sometimes you can't imagine everything.
Right. So I feel like for a lot of the property we want, we can think of the sandbox as kind of stress test one particular aspect, and we're isolating this one particular aspect from a very complex system. So one thing that will be missing is that when you isolate something out, if there's some interaction among among different elements, then that interaction might be missing from this one distilled abstraction, I guess.
Absolutely. That makes sense. Thank you.
Yes.
Okay, I'll move on in this question list. So I'm not sure if this is entirely relevant to what you're trying to solve, but it just made me think of this. So basically, the paper highlights that attention glitches persist even after applying various regularization techniques, like attention sharpening and the things you listed. So what do you think this suggests about just kind of in general, like the fundamental limitations of softmax based attention mechanism?
Yeah, great question. I do think that's quite inherent limitations. So, I guess like this for sharpening part, there we can see like, yeah. So here, I guess prior work they already found that if you can't, so like for some cases when you want very sharp attention, if you can't push it to be sharp enough, then you will have then you will have problem. If we are trying to target this particular problem, then we can find some fixes. For example, by trying to adaptively increase the temperature in the softmax, or by changing to hard attention. But this kind of thing, like changing it here, might affect something else. So I guess I do think it's a very inherent limitation. I don't have a good solution to this yet. Yeah.
No, yeah.
But
No,
yeah.
it's interesting that these things kind of bring up the fundamental limitations of different solutions. Yeah, that makes sense. And then I guess let's see. I kind of wanted to go back to the architectural changes that you did try to do to address this. So I guess there were multiple mechanisms contributing to attention glitches, like soft attention limitations, positional embedding failures.
Right.
Which of these failure modes do you think is most addressable through architectural changes?
That's a good question. Okay, sorry. Architectural changes could mean a lot of things. Like I think if we're
Yeah.
thinking that changing architecture from transformer to RNN or change transformer to something hybrid, then I think all of this could be solved in the sense that if we change to RNN, then we know that for this particular task, it solves it perfectly. If we're still trying to keep the attention structure, but then tweak some details, then it seems that I feel like at least from the things we tried, using relative positional encoding seems to be very helpful for denser sequences. But this one will not help on the sparser ones. And the reason is that, as we saw earlier, even if we're keeping the overall lengths to be the same, if we make the sequence sparser, we're still having a length, like implicit length normalization in the sense that now the distance between the write and the read is increased. And that would not be helped by relative positional encoding. So at least we know one case where it cannot be solved by this, but in practice, I think people found relative positional encoding to be quite helpful in various cases. Then I'm guessing in practice, we still have this inherent trade-off between different type of errors. It's just that it's probably harder for us to pin down what exactly are the trade-offs. Yeah.
Yeah, no, that makes sense. And yeah, that's just kind of a general question anyways. Thank you. And let's see, Q&A. So question from the audience. In most benchmarks, it does seem like attention outperforms stuff like LSTMs.
Yeah.
If you were to change the benchmark slightly, what modifications to the benchmark do you think will make attention perform better than LSTMs?
Oh, wait, sorry, are you saying like sorry, I thought the question is that like for most benchmarks, attention is performing better. And then are we changing standard benchmarks to still make attention perform better or changing the synthetic benchmarks?
It would like what changes to those benchmarks would make attention perform better than LSTMs?
Oh, I thought for most benchmarks, attention are already outperforming LSTM, right?
Oh yeah, you're right. Yeah. I think
I'm guessing the other way around, maybe.
yeah, maybe the other way around. Feel free to
Oh, okay.
try, but let's just talk about the other way around right now.
I see, yeah, the other way around thing. I think I feel like for this, it's probably good to reference the line of work on state-space models. So LSTM or like R in general, people know that it's not so like there are inherent limitations in terms of the expressivity, but the thing that people complain most in practice is that it's very unstable to train. So figuring out how to train things more stable and more efficient would be one way to resurrect these RNNs. And that's kind of exactly what this line of work in station models are doing. So they're trying to use different techniques in terms like both in terms of how to regularize, to normalize, and also how to combine with hardware design so that it can train a large recurrent model very efficiently and very well. And then over there, I feel like for tasks where those models claim to be better than transformers, in a lot of times they focus on extremely long range tasks. So this includes tasks on long range arena. For example, there's one task like the path X finding thing that could not be solved by any transformer by the time when Mamba came out. But the Mamba it's doing very well on it, even before Mamba the S4 models, for example. And then some other things that people are thinking could be quite interesting that again, also relating to the long context are going to be the naturally long cases. For example, when we have DNA data, genomic protein, these are very this kind of sequences where you have very sparse information in a very short sequence, but you start to see structure emerge in a long range. That's one thing that could be interesting. Another thing I want to mention is that I think from talking to people, it seems that currently for a lot of the natural language tasks or like reasoning tasks that we care about, if you train a status model from scratch, then they are not outperforming transformers. But if you can somehow solve the optimization problem, for example, by distilling from a bigger model, then you can improve drastically the performance on these kind of recurrent models, including that SSMs.
Cool. Thank you. That really answers the question. So I want to let the audience know that we have time for 1 to 2 more questions. If you've been holding them, let us know. I think one of the things that I always like to ask researchers toward the end is, from what you've seen, how has your work been received? And you covered a little bit about future directions, but what directions is this work going in already?
Oh, okay, I see. About received, I think I feel like this so in this talk we mentioned 2 papers. One is the prior paper and the other is this one. So the prior work is the transformer learn shortcuts to automata. I think one thing I find quite interesting is that even though we state clearly that shortcut is not a bad thing in our context, a lot of people mistaken that as the shortcut in empirical world, in the sense that it's some spurious connection to the feature. That's kind of not what we meant, but that's one misconception. But still, I think that work is quite well known. It's the most well from my line of work. And then this particular paper, I was quite excited about it. I think it's less well known. When talking to people, I think some of them will find this interesting, some find them too toy. And I think to me, one thing I always wanted to try, but I've been procrastinating on it, is to see which choice of data would allow us to train a transformer properly. So I guess in the work we mentioned that data seems to be the most promising direction. Okay, so data and also the model.
Right.
Architecture side, I guess currently I tend to believe that maybe a hybrid would be a good solution in practice. Then from the data side, I think we know that choosing the correct data will help training drastically. And this is one clean sandbox where we can actually afford to quite thoroughly or like quite exhaustively try different combinations of data, which is something I want to do, but I haven't.
Yeah, that sounds really exciting. And we'll watch out for it. So with that, we're pretty much at time. If there are any lingering questions, feel free to reach out to us via the Women in AI and Robotics channels, and we can connect you properly. But thank you so much, Bingbin, for your wonderful presentation. Yeah. And the AI reading group will take a pause in March, and we'll be back in April for everyone. So stay tuned to those announcements. But yeah, thank you so much, Bingbin.
All right, thank you, everyone. Thank you.